So in this video, I'll be covering about the concept of single source shortest path, that is using the Dijkstra's algorithm. So what is actually the single source shortest path, and what are the various algorithms related to the single source shortest path, and along with the example will be provided in this video. Single source shortest path, given certain of here the graph g equal to v comma e, where v indicates a set of vertices, e indicates a set of edges, and certain cost are being associated with each kind of here the edge. And the problem is to determine the shortest path from v to all other remaining vertices of the graph. So consider the graph which contains the source vertex, and there are various other vertices which are being present, like take for example v1, and similarly v2, and from v1 v3, and from v2 that is v4, and there are certain edges which are being present in this kind of the graph. The single source shortest path indicates from the given source. You can take any kind of your this source, and in this graph I'm considering the source to be equal to s. So from s, in order to reach to v1, of course the edge costs are also being associated, something like a 2, 6, 8, 4, 9, 10, 11. Certain kind of cost of the edges are being provided. And the problem of the single source shortest path is to find the shortest distance that can be reached from the source vertex, that is s, to all other remaining vertices, that is s to v1, what is the shortest distance, s to v2, what is the shortest distance, and so on, for how many number of vertices that are being present within the given graph. That is the problem of single source shortest path problem. It doesn't mean that you have to take only this s as the source vertex which you need to start from. You can also take any kind of here the other vertex and consider that as the source vertex, and from that particular vertex, you know, reach to all other kind of here the vertices, what is the minimum distance. So it is assumed that positive weights are to be taken into the consideration, and how this problem can be solved using the greedy approach. So it works by maintaining a set of yes, we can call it as a solution set or the special vertices set, whose shortest distance from the source is already known, and non-special vertices are to be observed into yes. That is, at each kind of your the iteration, you'll be identifying what is the shortest distance that can be reached from the source or from the previous vertex, and that is to be taken within the case of the solution set. And the remaining vertices, how this can be represented, that is v minus s, that is v indicates a set of vertices minus s, that is whatever the vertices that you have considered within your solution set. So after subtracting this one, whatever the remaining vertices that are being present, for those kinds of here the vertices, we can solve using the greedy approach using certain kind of here the condition. The condition which involves, that is, if distance of w is greater than distance of u plus cost of u comma w, then there is an update distance. If this condition is the true condition, then you need to update that kind of here the distance of the vertex, that is w, which is being given by distance of u plus cost of u comma w. So single source shortest path problem can be solved using two different kind of the algorithms. The first one, that is Dijkstra's algorithm, and the next one, that is a Bellman-Ford algorithm. So in this particular video, I'll be covering about the Dijikstra's algorithm and as well as the example and how these values are being obtained by tracing the algorithm. And the Bellman-Ford algorithm, that is, we can compare these two different algorithms in terms of here the time complexity. So the time complexity of Dijkstra's algorithm is been given by big O of E plus V log V, and whereas the time complexity of Bellman-Ford algorithm is given by big O of V into E, where V indicates a set of the vertices and E indicates the number of edges that are being present. So we can say Dijkstra's algorithm is quite faster as compared with the case of the Bellman-Ford algorithm due to its respect to time complexity. And this algorithm is related to Dijkstra's algorithm, that is to find the single source shortest path algorithm, that is which uses Dijkstra's algorithm. So this algorithm, that is algorithm shortest paths, there are certain parameters which are being indicated. That is v, cost, dist, and n. So v indicates it is the source vertex. V indicates the source vertex. Cost indicates the cost adjacency matrix, and dist indicates the resultant part. This is where your values are being stored after completing this kind of the algorithm. Whatever the values that are being stored within your distance array, those indicates the shortest distance that can be reached from the source vertex to all other remaining vertices. And n indicates the number of the vertices. N indicates the number of the vertices. So according to this kind of the algorithm, for I equal to 1 to n, do s of I equal to false, distance of I equal to cost of v comma I. That is for the given vertices, like for example, n equal to something like your 6 vertices are being provided, and you're making this s of 1 to be equal to false, and similarly s of 2 to be equal to false initially, and so on for how many number of vertices that are being present. So according to our consideration, there are 6 vertices. So s of 1 to s of 6 is made to false, and at each iteration you'll be also considering that is distance of I equal to cost of v comma I. So when you take the I value to be equal to 1, then this indicates s of 1 is equal to false, and distance. So distance of 1 is given as cost of v comma I. V indicates the source vertex. That is, assume the source vertex to be equal to 1 and the value of the I. So basically there are 3 values that may be generated within the case of the cost adjacency matrix, where you may encounter such as for example 0, infinity, and certain kind of the value which indicates the cost adjacency, that is edge cost, something like your 10 or any kind of the value. What does this mean? That is for example, this is your source vertex A, and from A we can reach to B, and from A we can reach to C, and similarly something like your D, and something like your E, and so on. There are certain number of the vertices that are being present. So from A to B to reach something like your 10, and from A to reach to C, something like your 4 is being given, the edge cost. So here cost of A comma A is given as 0. Similarly, cost of B comma B will be equal to 0, cost of C comma C equal to 0. And how can you get this kind of the 10 or any kind of the value? That is, whenever you need to calculate, that is cost of A comma B, that is cost of A comma B, since there is a direct edge from A to B. And what is the edge cost? Edge cost equal to 10. That is what we can say about how a particular edge cost with a numerical value can be generated. So 0 is also been explained, that is cost of A I comma I. That is cost of A comma A equal to 0, cost of B comma A equal to 0, and so on. And when you consider about the infinity, what does it mean? That is for example, if you need to find the cost of from A to E, where there is no direct edge from A to the E vertex. In such cases, it is been set to infinity. These are the initial assumptions that are being made. So according to this kind of the algorithm, that is s of 1 equal to false, s of 2 equal to false, s of 6 for how many number of values that are being present is vertices are being present, it is being set to false. And the next one, that is distance of I equal to cost of v comma I, where you'll be calculating, that is distance of when you take the value of your I equal to 1, that is distance of 1 equal to cost of 1 comma 1, that will be equal to 0. Similarly, when you take the value of your during your next iteration, I equal to 2, that is s of 2 equal to false, and similarly distance of 2 is being given as cost of v. What does v indicates? The source vertex. Assume the source vertex to be equal to 1. And what is the value of your I? That is 2. So cost of 1 comma 2. If there is a direct edge that has been associated from 1 to 2, then represent it respect to value, something like a 10, whatever the edge cost that is been associated. And if there is no direct edge, then indicate this as infinity. And this process goes on for how many number of values, vertices that are being present. That is, in our assumption, n equal to 6. So s of 6 equal to false. And similarly, distance of 6 equal to cost of 1 comma 6, and whatever the edge cost that is been associated. And make s of v equal to true. That is, whatever the source vertex that you have considered. In our assumption, v equal to 1. So s of 1 equal to 1 equal to true, and then distance of v equal to 0. It doesn't mean that you have to take the same kind of the source vertex to be equal to 1. As I mentioned, you can also take any kind of the vertex and start from that kind of the source vertex and find what is the shortest distance that can be reached from the source vertex to any other kind of the vertices. And from the next iterations, that is num equal to 2 onwards, you need to choose u among those vertices, whichever is the minimum from your previous iteration. What does it mean? That is, from the above iterations, that is from the above loop, that is for I equal to 1 to n do, assume that you have got the value of the d, that is distance. That is, distance of 1 is equal to 0, distance of 2 is equal to 10, distance of 3 is equal to infinity, distance of 4 is equal to 4, and distance of 5 equal to something like infinity, and distance of 6 to be equal to something like 8 is been provided, which has been executed from the previous step. So these are the values of the distance at the first iteration. And among these values, you can exclude 0 because distance of 1, that is a source vertex, and you can also exclude infinity values which are being present. And from the remaining values, that is 10, 4 and 8, what is the minimum? Minimum is equal to 4. And what is its respect to vertex that is being present? That is 4. And that is how you need to take the value of your u to be equal to 4. And from the fourth vertex onwards, whatever the edges that are being present, adjacent vertices that are being present, check whether s of w is equal to false. If it is false, then check whether if distance of w is greater than distance of u plus cost of u comma w. If it is a true condition, update that kind of the distance vertex. And this process goes on for the values of num equal to 2 to n minus 1. That is what your algorithm, Dijikstra's algorithm specifies. So consider the example. That is, we have the, okay, one correction. This is B. And this is C. And this is, I repeat once again. This is your source vertex A, and vertex B, vertex C, D, and as well as E. So these are the vertices which are being present with respect to edges and with respect to number of the vertices. So what has to be done related to the algorithm? That is, you can take the algorithm by tracing, or like take, for example, you can take the columns. That is, during your first iteration, what is the iteration sequence number, and what is the special vertices or the solution set, and what is the vertex that you have selected, and for how many number of vertices that are being present. That is, here there are 5 vertices, namely A, B, C, D, and then E. These are the vertices. So the iteration, and similarly this, we have not yet taken any kind of the solution set vertices, and the vertex selected initially it will be equal to null. Nothing has been present. And coming to the next, that is distance of A. So distance of A equal to cost of 1 comma 1. As I mentioned, cost of A comma A, that will be equal to 0. From A to reach B, if there is a direct edge, then include that distance, that is 7. And similarly, from A to reach to C, there is no direct edge. So there is no direct edge that is being associated over to the C. Directly we cannot reach to C. So that is being set as an infinity. from A, can we reach to D directly? Is there any direct edge? There is no direct edge that has been associated. Similarly, from A to reach E, there is an edge that has been associated that is equal to E with the edge cost to be equal to 1. This will be the values of the distance array during your first iteration. And among these values, that is, as I mentioned, 0 should not be taken, infinities should not be taken into the consideration. And the next one, that is minimum, is 1. So yeah, 1. You have selected the source vertex to be equal to A. And what is the vertex that you have selected? The vertex that you have selected is E, because it is the minimum. And during your next iteration, find out if there is any updated value. That is, from A, can we reach to B? We can reach to B. We can reach to B with the value. That is, from A, we can reach to B with the cost to be equal to 7. Similarly, from A through E, can we reach to B? From A through E. From A through E, we can also reach to B. What is the cost? 8 plus 1, that will be equal to 9. What is the minimum? 7 is the minimum. So there is no change or update that is present in this kind of the values. That is distance matrix. And the next one, this is your E, and this is A. And from A through C, can we reach to C? From A through E, we can reach to C. The direction is A to E, and similarly E to C. What is the cost? That is 1 plus 2, that will be equal to 3. So there is an update. When you compare with infinity and similarly 3, which is the minimum, 3 is the minimum. So there is a new distance matrix, new distance array value for the C. That is distance of C equal to 3. In the same fashion, from A through E, can we reach to D? So from A through E, that is 1. Can we reach to D? We can reach to D. And what is the cost? That is 1 plus 7. That will be equal to 8. So 8 is the new updated value when compared with infinity and 8. In the same fashion, that is from A to E, because already we have taken this into the solution set, that is not been considered. And this process goes on for your next iteration. That is, during your next iteration, from the previous, we have selected E vertex, and among this one. So what is the new minimum value here in this case? That is 3 will be the minimum. So, and what is its respect to vertex? That is C. So C is being taken into the vertex selected. And find out, is there any shortest distance that can be reached if there is any updated value. So 0, it is the same thing. 3, it is the same thing. 1, it is the same thing, because we have made this as the true part. And the next one, that is, find out whether we can reach from A through E to C, or from A through E to B, we can reach. What is the distance? From A through E and also through C, can we reach to B? If it is, then find what is the distance. So if you consider this kind of this scenario, from A, so from A, we can reach to E and we can reach to B. That is with the cost to be equal to 9. That is A, E, B, the cost will be equal to 1 plus 8, that is 9. And from A through E through C, can we reach to B? From A through E and through C, can we reach to B? Yes, we can reach. That is A, E, C, and we can reach to B. And what is the cost? That is 1 plus 2, 3 plus 3. That will be equal to 6. That is A to E, E to C, and similarly C to B. That is 1 plus 2 plus 3. That is totally we have 6. So 6 is minimum. And what about the previous value of the distance of B? Previous value of the distance of B is 7. Now it has been updated with the new value, that is 6, because compared with 7 and 6, 6 is the minimum. 6 is been updated. In the same fashion, A, E, D, find the distance. And similarly A, E, C, D, find the distance. If you have the minimum distance, then it is to be updated. So when you take A, E, C, that is A, E, and then D. A, E, D. What is the distance? A, E, D. So A, E, D, 1 plus 7, that is 8. Similarly, A, E, C, D. A, E, C, D, that is 1 plus 2, 3, 3 plus 6, that is 9. So what is the minimum? Minimum is equal to 8 only. So it is unchanged. 8 remains the same thing. And during the next iteration, we have taken into the solution set A, comma, E, comma, C. And what is the vertex that you have selected between 6 and 8? The minimum is equal to, that is 6. So here we have to consider the next minimum to be equal to B. So B is the vertex that has been selected. And find out A, E, C. This is unchanged. It will be equal to same, that is 0. 6, because we have taken and made it this vertex to true, that is B to be true. And 3 remains the same thing. We have already found the shortest distance to C, and also shortest distance to E. So here A, E, C to D. A, E, C to D. What is the cost? 1 plus 2 plus 6. That is 2 plus 1, 3, 6, 9. That is 9. It is not the new updated value, because previously we have 8. And if there is any distance that is less than this 8, then you can have to consider that and place it within your distance of D. Similarly, the next scenario. The next scenario is A, E, C, B, D. A, E, C, B, D. There is no edge that has been connected from B to D. So you should not take that kind of a solution. So 8 remains the minimum value here. And during your next iteration, that is A, comma, E, comma, C, comma, B. And since we have already finished distance of B as a minimum distance, and one is, E is already been completed, C is already been completed, because we have made it to true, and the only remaining vertex is D. Find out, is there any other shortest distance in the similar fashion that I have said in the previous case, that is A, E, C, B, 6, 3, 8, and similarly 1 will be the final values. What can you interpret based on these kinds of the values? That is, from A, we can reach to B with the distance to be equal to 6. From A, we can reach to C with the distance to be equal to 3. From A, we can reach to D with the distance to be equal to 8. In the same fashion, from A to E, we can reach with the distance to be equal to 1. We can also cross-verify the same thing. That is A to B, that is already we have, here you can observe A to B is equal to 7. And what is the new updated value? That is from A through E, that is 1 plus 2 plus 3. You not reach this kind of the 6 value, that is A to E, A to C, and then C to B. What is A to E cost? That is 1 plus E to C 2 plus C to B, that is equal to 3. Because as compared with 7 and 6, 6 is the minimum. So here we got the new minimum value, that is 6. And similarly, A to C. So A to C with the cost to be equal to 3. And what is this respective path? That is A to E to C. That is 1 plus 2. That will be equal to 3. And how about this D with the minimum distance to be equal to 8? That is, what is the path to be taken? A, if you consider about to reach to D, that is A, E, D. And what is the cost? That is 1 plus 7, that will be equal to 8. That is A to E, E to D. And how about the case of E? Because there is a direct edge that has been associated, 1. And this is how we can say the shortest distance can be found using the Dijikstra's algorithm. Now consider another example. So within the another example, consider I'll mention this in your next slide related to the single source shortest path. So this is how the single source shortest path can be implemented using the Dijikstra's algorithm.